Okay, so this is going to be a review of binary representation for the IB Computer Science exam. First, let's take a look at what the curriculum says about this. So this is located around page 24 of the IB curriculum. And down here, whoops, on page 24, oops, my apologies, it says the following has to be done. So we're going to do what's in this section of the curriculum, and what I did is I quickly copied it over to here so we can take a look at it. So we're going to define the terms bit, byte, binary, decimal. This word denary is just another word for decimal, okay? So we don't need to worry about that. Decimal is a better word, and hexadecimal. And we're going to outline how data is represented on the computer, including all kinds of different formats as it outlines here in the curriculum point. Okay. If you remember, we are dealing with a two-state binary dual system. The hardware incorporates this, but we're not really talking about the hardware here. Code is translated into this two-state system, and then the hardware executes it. What needs to be translated is the data, which are the code, your instructions, as well as the data that your code needs. Okay? The hardware works with it, and the two-state system needs a way to represent this data. So here's how it's represented. The simplest piece of data is a Boolean data, an on-off, true, false, plus, minus, yes, no, 0, 1 type of data. And we know that's how the computer represents things. So when we make a Boolean variable, it translates directly. Moving up from there would be integers. Integers aren't just true, false. They have quantity values. Now, those quantity values, as you're going to learn, have a representation in binary, and I'm going to show you how that works. Doubles is a little trickier. With the doubles, it basically divides the double into two parts. The whole number portion and the decimal portion, and then both are stored as binary numbers. You don't really need to know exactly how that works yet in this curriculum. Just know that that's essentially how it works. Characters are represented by a lookup table known as the ASCII table. I'll show you more of that in a minute. Strings are arrays of characters. So if characters can be represented as numbers on a lookup table, and numbers can be represented as zeros and ones, then we're starting to represent everything as zeros and ones. If we go beyond strings into more complicated things like classes, classes are made up of primitive objects. So these things, strings and classes, are represented by the more simple objects like characters, doubles, integers, and booleans. All right, so the summary is everything is based on binary two-state values. If we look at numbers the way we think of them, and we think of them in the decimal system or a base 10 system, because we use 10 digits to represent our numbers. Whether those numbers are fractional or decimal numbers, really, if we looked at the math behind it, we'd be multiplying by the base 10 and then raising things to certain powers and combining the numbers that way. This would be true for any type of number in our system, but we are now working with a base 2 or a binary system. So let me jump back real quick. That's what it means by the terms decimal system versus binary system. The terms bit and byte mean a bit is just 1 or 0 in a two-state system, or on, off, true, false, whatever. That's what a bit is. It's a bit of data. A byte is 8 of those. Okay? So when you put 8 together, 8 bits, you get a byte. Okay? So that's already starting to come together. We'll put hexadecimal in place in a second. All right. This is the easiest way to start remembering this stuff, this particular chart. And I would recommend you just copy it down if you see one of these types of questions. It's your guide. It's your helping thing. What you're going to put down is the first 16 numbers that you know, starting at 0 up to 15. From there, write a 4-bit, okay, 4-bit binary equivalent. And what you can do to get these binary numbers is look for the patterns that I'm describing to you. So the simplest way to think of it might be to just count the way you'd normally count. 0, 1, but you can't write 2 because the only digits you have are 1 and 0. So the next number that comes up is 10, then 11. Then you can't do 12, you can't do 13. The next number that would come up is 100, then 101, then 110. Next number that would come up, 111, then 1,000, etc. If you count that way, you'll get the bit sequence down. Another way you can look at it is by going in rows. These two go 0, 1, 0, 1, 0, 1. So it just toggles 0, 1, 0, 1, 0, 1, 0, 1. The next row over, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, then 4 zeros, 4 ones, 4 zeros, 4 ones, then 8 zeros, 8 ones. So as it lists here, there is a number of different ways you can basically remember that chart. Okay? This chart then becomes your guide later to help you with some of these types of questions. Here's the process of converting numbers in our base 10 system into base 2 system. So from decimal to binary. You divide the number by 2, okay? And you get the answer and the remainder. Excuse me, I'm going to sneeze. There we go. This will continue. You'll keep dividing it by 2 and getting the remainder and the answer. And you keep going until you reach 0 as the number that's left over when you're dividing, and that's when you stop. And then you collect all the remainders you have, because always the remainder is either going to be 1 or 0, and you put them together to form the binary number. Now, if it just so happens that they say it's something like a 2-bit memory register, then you might have to put a bunch of zeros at the front to pad it in to fill in the missing spaces at the front. We're going to do an example in a second. Okay? Those would be just leading zeros. You can always have zeros in front of a number. Now, if we go back the other way, so we start with a binary number, okay, and we want to go back into base 2. Now what you do is you write the binary number going down, starting at the front, so right here's the front, and then right going towards this, going towards the right. So you write it down, and then here's what we do. We start with a 0, multiply by 2, which is the opposite of dividing, right? And add 1, and the 1 comes from the sequence here. The answer we get from this little piece of math then moves to the front of the line for the next digit. So maybe look at it over here. 0 times 2 plus 1 equals 1. The 1 shifts over. 1 times 2 plus 0 is 2. 2 shifts over. 2 times 2 plus 1, 5. 5 shifts over, et cetera, et cetera, et cetera. Eventually we get back to our original number. We're going to practice this in a second. Okay? Now, hexadecimal is an in-between state between base 10 and base 2, because now it's using 16 as the possible digits. How does it use 16? Well, it uses numbers 0 to 9 and then letters A to F. So I'm just going to fit that right into our chart right there, in between. Right, so here's decimal, here's binary, here's hexadecimal in between. Notice that in binary, I needed 4 digits to represent numbers up to 15. In our system, I needed 2 digits to get all the way up to 15. But in hex, I'm still only using 1 digit to get all the way up to 15. Here's how you do it. You use this chart as your guide. Okay? So if it says, take the number 2A5C and convert it to binary, you just look them up on the chart. What's 2? Oh, it's this number right there. 2 is 0010. What's A? Oh, look it up on the chart. It's 1010. So I'll just pop it in there. What's 5? 0101. What's C? 1100. Put them all together. I get 2A5C is 00101, et cetera, et cetera, et cetera. So it's just that easy when you use the chart. And it's also that easy to go back. Because if I'm given this binary number, I can start grouping them off into 4s and looking them up on the charts and getting the same number back. Now, how could I go to decimal? Well, again, you're using hex as an in-between. So you can go from that one, whoops, to the other one by just going in between. Okay, so let's try it. Does anyone remember the one that was on the exam a second ago? Or give me a hexadecimal number.
It was 3B.
3B. Okay, so let's do that. 3B, and let's say what's the decimal version of this. But let's start by turning it into binary. So I look up 3 on the chart. Here it is. Okay, so 3 is 0011. I look up B on the chart. Here's B. 1011. But as if I recall, didn't it say it was a 2-byte register? Let's say it was. I can't remember what the question said, but let's say it was a 2-byte register. How many bytes is that right now? That's just 1 byte. So to make this a 2-byte register, I've got to pad in some zeros there. So let me pad in 8 more zeros. Okay? So I don't know why they'd ask you that question, but let's say they did. You'd have to put in some padding there to start it off. Okay? So there, now we've got it all padded in. That's a 8-byte. But we want to turn this into decimal number. So remember, the way we do it is we can start at the first one. We actually don't need to start at all the zeros. And we write that number going down. 1, 0, 1, 1. Okay? That's me starting there and writing this way. Okay? I could actually do it with all the zeros if you want, but what you're going to find is it just keeps generating a 0 and then a 0. Because you start with this. You go 0 times 2 plus 1 equals. Now again, imagine that was a 0. It'd be 0 times 2, 0, plus 0, 0. Then 0 times 0 plus 0. It would just keep giving you a 0. So it's good to start at the first one. Okay? Then this part of it, times 2 plus 1 equals, that part right there is going to repeat all the way down. So I'm going to use the power of the smartboard here to save myself a little time here. Okay, see what I mean? That's going to keep going. What we need to do here is generate our answer. So 0 times 2 plus 1 is 1. This moves over here. 1 times 2 plus 1. 3 times 2 plus 1. 7 times 2 plus 0. 14 times 2 plus 1. And finally, 29 times 2 plus 1. Oh, seriously? 59. Okay. So we've converted base 16 into base 10. Okay? We've converted hexadecimal into decimal. But let's kind of test our math. Let's imagine we had to go back the other direction. Let's say, actually, let me do it this way. I'm going to insert a slide here. Let's say you were given the 59. And they said, what's the hex? Okay, how would we do this? Let's turn it into binary. So let's start with a 59 and divide it. Divide it by 2. What do we get? 59 divided by 2. It's 28. Remainder, 1. All right. 2 into 28. Remainder, 2 into 14. Remainder, 2 into 7. 2 into 3. Now here's the one that throws you out. 2 goes into 1 0 times, but has a remainder of 1. Okay? We take this binary number and write it, but now we start at the bottom and go up. So 1, 1, 1, 0, 0, 1. Let's take a second to go back and see if we got the same binary number as we did back here. 1, 1, 1, 0, 1, 1. Okay, so one thing seems to be missing here, right? Where did we screw up? Yeah. So the error was here in your mental math, that this is 29. Okay? 2 goes into 29 14 times, but this is a 1, right? So it makes this a 1 right here. And now let's go back and check. Now it matches. Okay, now it matches. So we made a little minor error there. Okay, but now we have this binary number. Let me rewrite it. 1, 1, 1, 0, 1, 1. And we're going to go to hex. Okay, so the way to go to hex is group off 4 digits. Group off 4 digits. If I don't have 4 digits, what do? I pad it with zeros. Okay, so I have this 4 digits and this 4 digits, and I need to look them up on my chart. Now, I don't have the chart here, but I can tell you what they are. 3B, because that's what we said we were going to get. And let's just double check. Is 0, 1, 1, 3? Yep. And is 0 or 1011B. Yep, it is. Okay? So that's the process of going back and forth. Finally, what if we are doing something other than numbers, like letters? This is the ASCII lookup table. So for example, the letter H, capital H, is hexadecimal number 48. It is binary number 010010000. It is decimal number 72. Okay? The letter lowercase k is 6b in hex. Or it's just a lookup table, so then it can just use that, so it just looks it up in terms of the number that's there. So that's what it does in a lookup table on your computer to turn letters into numbers. What about pictures or sounds or videos? Well, anything that gets more complex than that, it starts taking individual pieces of data and converting it eventually into binary values. So here's an example. Here's a simple graphic right here, the little happy face. If I put that onto a matrix, a grid, and I have that same graphic on the matrix, now I know where each spot is either white or black in my drawing. So first thing I'm going to do is remember the dimensions of my matrix. So this is a 9 width, 7 height matrix. So if I take that height and width, 7 times 9, and convert it to binary, I'd get 7 times 9. And then if I remember how many colors I need, well, just 2 colors here. That's the number 2. I now have a bunch of binary data that would represent the header of this. So 2 bytes of data to remember the dimensions, height and width, and the number of colors. Okay? Then I'd remember the actual data. Now because it's just 2 colors, I could basically just remember zeros and ones for the whole thing. Put together the header section, maybe I need to pad it with some zeros, and all the rest of the data, I can basically just take that series of ones and zeros and turn it back into this simple graphic if needed. The more complex the graphic, obviously the more binary data I'm going to have to produce. Okay? And that, kids, is it.